All right, so let's get straight to it, guys. Hope everybody's doing well today. So, what I'm going to do in this video, a little bit different from what I've been doing on my research series, is I'm actually going to talk about my final research presentation that I did for my computational physics class. So, for a lot of upper level physics classes, you'll actually do like final presentations and final papers as opposed to final exams, especially with something like computational physics, because a lot of it is just, running and writing code, doing projects. And so there's really not much of a final exam to be had. Um, the other class that I had a final paper for was my nuclear physics class, which was an upper level elective. So instead of having tests and a final exam. We actually just had a semester long research project, which I'll be making a video on sometime in the next few days. But today, I wanted to talk about my computational physics presentation. It's really interesting stuff, in my opinion. So, what I did the presentation on is a topic called quantum chaology. And so, we're going to dive headfirst into that today and hopefully have some fun. So, quantum chaology is a subfield of physics. It kind of is a collection of a few different overarching fields of physics. One of those would be quantum mechanics, hence the name. And another field of physics that it touches on is chaos. So, the main goal of quantum chaology, as you can see on the slideshow here, is to try to bridge the gap between what we call classical chaos and quantum mechanics. So, chaos or chaotic motion is defined as classical theory, right? So it obeys the laws of classical mechanics, and so the reason that quantum chaology came about is because physicists in the 80s started thinking, well, quantum mechanics is supposed to underlie classical mechanics. In other words, you can derive the the equations of motion and the laws of classical motion um, through quantum mechanics. If you just let the principal quantum number get larger and larger, which we'll talk about in more detail in the next slide. And so basically the idea of quantum chaology is, hey, let's look at some classical systems that have chaotic motion and basically see what things look like at the quantum level for those types of systems. And so just to go ahead and define chaos real quick for anyone who's not familiar with it, the basic idea is that you have these systems that are extremely sensitive to initial conditions. So a great example would be something like the double pendulum, where if you release two double pendulums from slightly different initial conditions, whether it be initial speed or slight variations in initial angle, the motion of those pendulums is going to diverge. The comparative motion of those two double pendulums will diverge from each other at a certain time. And another example of this is actually the motion of the solar system. So in the solar system, we can predict the motion of the planets up until a certain period of time, essentially. So once we hit, further and further time scales trying to predict the motion of the planets, we actually lose the ability to do that because the motion of the planets is chaotic. And so, one other one that I want to point out, because it's funny in my opinion, is actually the weather is totally chaotic system. Trying to make meteorological predictions on the weather is only feasible up until really like about a week or maybe 10 days at most. And that's why, some people complain, oh, well, they said it was going to rain today. And so I canceled my plans and now the sun's shining. And, they think that the weather people don't know what they're doing. But the truth is, the weather that they give you, the predictions that they give you are really just, you know, the best approximation that they can get because the weather systems are chaotic and one tiny little change in the atmosphere or in the conditions can drastically change weather. So that's chaos. Quantum mechanics is just the study of subatomic and atomic phenomena. Um, it's a different type of mechanics because physicists realized in the early 1900s that you can't describe things very, very small, like atoms and molecules and so forth, with classical mechanics. It just doesn't work. And we'll talk about why here in a minute. So, the way that quantum chaology wants to try to bridge this gap between uh, classical chaos and quantum mechanics is using this thing called Bohr's correspondence principle. So you'll see on the right here, we've got Niels Bohr having a chat with Einstein. Those two famously love to argue about quantum mechanics. And Bohr's correspondence principle basically tells us that as you increase your principal quantum number n, higher and higher, the laws of quantum mechanics should contain the laws of classical mechanics. And the main difference between quantum mechanics and classical mechanics is this idea of discretized energy. So if you've ever taken chemistry, then you would be familiar with what's called atomic orbitals. And the idea is that these electrons orbiting in the atom can only take on discretized energy amounts. Um, and basically what that means is that the electron is going to orbit at a fixed energy. It's not going to, it's not like a ball rolling down a hill where the kinetic energy is continuously changing as the ball gets closer to the ground, right? However, if you increase this quantum number, the spacing between the different energy levels in which the electron can sit in become closer and closer and closer. And when you reach a certain point, what's called the semi-classical range, all the laws of quantum mechanics still apply. However, your energy levels are so close together that you can essentially call them a continuum at that point. And then now the laws of classical mechanics also apply. So you can say, look at an electron's orbit using quantum and classical mechanics. So that's kind of the regime that we're going to be working in, this so-called semi-classical range, where we can apply both of these theories. And this semi-classical region of physics is a very interesting field. Lots of research has gone on in that area. So one of the things that I need to point out is this idea of chaology instead of chaos. So, like I said, looking at previous slides, is chaos is defined classically as sensitivity to initial conditions, and the idea is that if you didn't have infinite precision, then there's no way you could make predictions into the future about these chaotic systems. And that's because in a chaotic system, you could change your initial conditions uh, infinitesimally, is the formal term for it. That basically means you can make tiny, tiny, tiny changes, and your subsequent motion will still diverge uh, at a certain time. And one of the reasons why it's been coined quantum chaology and not quantum chaos is because it's not really the same thing as classical chaos, because we have this thing called the Heisenberg uncertainty principle. And so, what this Heisenberg uncertainty principle means is you can't make those kind of infinitesimal changes in your initial conditions because you just don't know that much about a quantum system. So, what Heisenberg figured out in the 20s is that the more you know about a particle's position, the less you know about its momentum or the opposite is also true. The more you know about its momentum, the less you know about its position. And so if we were to try to make infinitesimal changes in our initial conditions, we just wouldn't be able to do that because we just can't know that much about our quantum system. So that's the distinction between chaos and chaology. And it's important to understand that chaology is a better term for what we're studying here because the stuff we're going to look at isn't formally chaos. It's just kind of chaos adjacent. It's the way I like to think of it. So the system we're going to look at, just to try to give a brief introduction to the kind of calculations we're going to be doing and the kind of systems we're going to be looking at. Let's look at something that's called an infinite square well. So when I took my introductory quantum mechanics class, Modern Physics 1, the first quantum mechanical system that we learned about to try to kind of understand the weirdness of quantum mechanics is this thing called the infinite square well. And basically, what it is you have a particle that is confined to some infinite potential well, which just means that it's confined in this region L, and it can't escape that region because the potential walls around it are infinite. So it has no way of escaping those walls. And this is also what's called Dirichlet boundary conditions, which means that the wave function, it's imposed on the wave function that it vanishes at these potential boundaries. And so these waves that you're seeing on the left basically just represent the different wave function modes or stationary states at different energies. And so on the right here, you see the probability distribution, and that's more so what we're going to be looking at. And basically, what that means is um, if you have this particle confined to this one-dimensional well of length L, these wave functions, when you square them and integrate them over the length of your well, you can generate a probability distribution. And what that means is if you ask, okay, where's my particle inside of my well at a given time? Well, at the energy level n equals one, if you were to look, the highest probability is that it's somewhere in the middle, but you could also find it, somewhere to the left out here, somewhere to the right. Subsequently, it's the same thing as you go in increasing energy levels, just the probability distribution changes. And that's basically what we're going to be looking at here in a minute. So the classical system that we're going to be taking a look at is this idea of classical billiard balls. So the idea is you confine a classical particle, right, like a billiard ball, to some shape, right, with these same kind of boundary conditions, just a little bit different. Basically, the ball is not allowed to leave the shape that it's in, and it will elastically scatter off of all of these walls that it's confined in. And so it turns out if you have irregular shapes for the geometry that the ball is confined in, you can get chaotic motion. And so you can see that here in example A and over here in the left corner. And basically what that means is that, if you release two pool balls from slightly different uh, positions inside of your shape, their trajectories through time would rapidly diverge from each other, which is different from this symmetric shape over here. This is actually just a circle. The centerpiece right here comes about just through the trajectories. That's not actually a wall. And so the idea is that if you have a symmetric shape, your motion isn't chaotic, it's regular and predictable. However, if you have some type of irregular shape, like what's called the Bunimovich stadium, you get chaotic trajectories for your pool ball. So you can use this kind of infinite square well idea and do the same kind of thing. This time it'll be two-dimensional. And so the idea is that we're going to confine our particle into a circular shaped well. with Dirichlet boundary conditions as well that impose that the wave function vanishes at our circular boundaries. And then what we can do is we can establish a wave function for that circular boundary and essentially generate the probability distributions in Python, um, just solving the wave function numerically and generate the probability distributions for the shape. And as you can see, the probability distributions look weird, but they are not chaotic. So these solutions could actually be derived by hand, essentially. Um, they're mathematically attainable. You don't have to run code to find these probability solutions. They're analytically solvable. The wave functions are square integrable in this system. And you get some really interesting distributions for sure, but they're all um, what's called, I guess, regular probability distributions. They're, mathematically uh, attainable. You don't have to run it in a computer to figure out what the probability distribution would be. And so that makes sense because our classical analog is regular as well. So our quantum analog is also regular. So, however, just like with our Bunimovich stadium shape in classical uh, billiard balls, in our quantum billiards, we get irregular probability distributions when we confine our quantum particle into a Bunimovich shape with our Dirichlet boundary conditions. And we get a couple of weird effects that we're going to talk about. One of the first ones is that you have these irregular distributions of your probability uh, distribution, and it's not analytically solvable. So, in other words, if I wanted to know what the probability distribution for my particle would be at this energy state that I've coded up, I would have to run it in a coding software like Python. I couldn't analytically solve the pen and paper what the probability distribution would be for my particle because it is in this chaotically shaped geometry. It's confined to this chaotically shaped geometry. And so we only get numerical solutions for that. And you can only figure out the probability distributions, like I said, by just running the code. And we get this really interesting effect, what's called scarred wave functions. And so in this diagram here, you'll see that the spots of yellow and orange and pink represent areas of high probability for the particle to be found. And then the dark purples and blues and black are regions of low or no probability to find the particle. And what I mean by wave function scarring, you'll notice is that we have this stadium shape, but most of the regions for high probability are just condensed in this strip here across the middle. And that actually corresponds to a classical trajectory that you would see in the Bunimovich Stadium. So if you look over to the left at our Bunimovich Stadium, you'll see that you've got some lines coming across from the flat wall on the top and the bottom that just kind of bounce back and forth a few times before maybe they run into a curve and scatter off somewhere else. And you can actually see that classical trajectory is kind of coded in a sense to this quantum probability distribution when you have a particle confined in the same kind of shape. And so you can see that scarring more here in these uh, probability distributions pulled from a paper that I read while I was researching. This one here is from my own code. Um, and you see these scars where the probability distributions kind of uh, sit in these classical trajectories. It's very interesting. Here's just a few more of those probability distributions at different energies. And yeah, so there's really not much else to say here other than just you can really see the scarring show up on this graph right here. This is one of my favorites. just huge amounts of scarring right across the middle, and you can see that that corresponds to this bouncing back and forth here in the classical analog. And so one of the cool applications of this quantum chaology idea is is being used right now in what's called mesoscopic physics. And mesoscopic physics is something that is in the semi-classical region, right? It's the region between microscopic and macroscopic physics where, you know, quantum and classical physics are applicable. And what it's being used for here is to try to predict changes in conductance in a graphene semiconductor cavity. And so what these physicists did was they said, okay, well, our graphene semiconductor cavity has one of these, you know, uh, chaotic geometries, classically chaotic, and irregular probability distributions in the quantum analog as well. And so what they did was they said, okay, we're going to run a simulation and take a look at where these wave function scars pop up on the right here and see if that corresponds to our change in conductance that we find in the actual physical experiment here. And what they saw is that it actually was a pretty good predictor of where these changes in conductance would pop up. And so that's how it's being used today. But that's pretty much all I've got to say on it now. So I hope you guys enjoy. And if anybody would like for me to maybe go into more detail or talk about some research papers, be more than happy to do so. But I hope everybody is doing well, and I'll see you guys next time.